Welcome back. In this video, part 3 in the series, we'll be looking at the details of the z-test for one proportion. I'm assuming that you've already watched parts 1 and 2, so you're familiar with how to set up a pair of hypotheses and how to choose a level of significance. This video will be a little bit longer because we're going to cover the remaining 5 steps of the process for the test of proportion. All right, I'd like you to read the situation below. Try to discern what parameter would be relevant to test. Is it a mean or a proportion, and of what? And then once you've figured that out, set up a set of hypotheses to test the claim that's put forward in the statement. Pause the video if you need to, and then you'll be able to check your answer. All right, hopefully you've got this answer below. So reading this paragraph here, there's a study where smokers were trying to quit using the drug Chantix. And we have a count of how many were successful after 6 months. So participants then were classified as either successful or not successful. So with this categorical data, we should be testing a proportion. The proportion of what? Remember, we're testing a population proportion. So if our study is just some smokers who tried quitting with Chantix, we hope to be able to extend these results to the population of all smokers who quit using the drug Chantix. All right, so we're testing this proportion P. That means that it's going to go on the left-hand side in both our hypotheses. And on the right-hand side, we need some number to compare against. Well, we're given this background information that in general, 4% of smokers who try quitting are successful after 6 months. So that's going to be what we compare this proportion against. We do need to convert this percentage to a decimal so that it's a fair comparison because proportions are in decimal form. So that 4% we'd convert to 0.04. So the null hypothesis is basically saying, hey, even when people take Chantix, they still only have a 4% chance of being able to quit successfully. But if the drug is effective, it's going to help people quit. So the proportion who are able to quit would be greater than the ordinary 4%. Maybe not everybody, but that a greater proportion would be successful. Okay, a little bit more review. So if these are our hypotheses, I want you to describe what would a type 1 error be. Talk about smoking and what we think is true about this drug Chantix, and then do the same for type 2 error. Okay, so recall a type 1 error is when we reject the null hypothesis and support the alternative hypothesis when the null hypothesis is actually true. So our test leads us to believe that this drug is effective, but it actually really isn't. The opposite type of error, a type 2 error, is when we fail to reject the null hypothesis when we should have because it's the alternative that's actually true. So that would be the scenario where we fail to detect that this drug actually works. All right, in the part 2, we talked about selecting our significance level, alpha. Now, some of this is personal preference, or it depends on your stake in the situation. So I have 3 statements here, and each of them aligns with a particular significance level, 1%, 5%, or 10%. So pause the video and see if you can match up which statement goes with which alpha. All right, here's the correct answer. So remember, a small alpha, like 1%, is going to require the strongest evidence before we can reject the null hypothesis. So that is, we would need to have overwhelming evidence that there actually is an effect, that Chantix helps, before we prescribe it to people. At the other extreme, 10% is going to require the least amount of evidence. So that matches up with the middle statement because here, we consider that smoking is just so bad for you that we're willing to try anything, even if the evidence is not especially strong. And then the statement in the middle is kind of a little bit of both. We acknowledge that, yeah, we don't want people smoking, but then again, if Chantix is expensive or has other side effects, we wouldn't want to jump to use it without at least a good amount of evidence. So in that case, the intermediate alpha of 5% would be appropriate. Okay, so depending on you and your personal preferences, you could really make a case for any of these significance levels. Just for this video, I'm going to go with 5% and kind of acknowledge both sides of the coin. All right, so before we do step 3, we've really got to take a little peek at step 4. So that is, we need to know what test we're going to be doing. If we're testing a single proportion P, like we've got in our hypotheses, just go ahead and tell you that the so-called test statistic we're going to use looks like this. It's a Z statistic. All right. So depending on your test statistic, it's only going to work, give us the correct verdict if some certain conditions are met, or at the bare minimum, if these conditions can be assumed to be met. Okay. So we can't just use a Z-test any old time we feel like it. We've got to check a few things first. All right, so we check those things in step 3. We check the necessary conditions that we're able to check. And if there are any that we're not able to check, we have to clearly state what it is we're going to assume in order to keep moving forward. So for our Z-test of proportion, there's 3 things we need to worry about. In a nutshell, we'll call these normality, independence, and random sample. So that is, we're going to be using this Z statistic. Now, if you recall, the Z distribution is a normal distribution. In fact, it's the standard normal distribution. So in order for this to work, we need to know that the shape of this distribution, had we performed this experiment many, many, many times, is normal. So when would that be a good assumption? If you remember from the sampling distribution for proportion, there are a couple rules of thumb. And if both of these are satisfied, then it's a good assumption that this test statistic would have a normal distribution. Right, so the calculations we're going to do is take our sample size n and multiply it by the hypothesized proportion. This is the number in your null hypotheses. So if that product is at least 10, you're in good shape. But we also need this other product to be at least 10, our sample size times 1 minus the hypothesized proportion. Okay? So if both of those are 10 or above, then you can assume normality. All right, next, independence. So if our population has been sampled without replacement, which is probably the case here, we didn't let smokers participate in the same study more than once. So they didn't have the opportunity to be selected more than once. Then we need to check that no more than 10% of the population has been included in our sample. Right, so setting that up in a mathematical expression, we want our sample size, little n, to be less than or equal to 1/10 of the population size, big N. Right? Our third and final condition, probably the most straightforward, we're trying to use a sample to say something about the whole population. So if we start with a biased sample, we're really not going to get any good information at all. So if our sample was randomly selected, then we can be relatively assured that it's going to be representative of the whole population. All right, so let's apply these to the smoking example. So what numbers would we multiply here? Well, our sample size was that the study included 380 smokers, so that's little n. And the hypothesized proportion was 4%. We found that in our null hypothesis. So multiplying that out, we get 15.2. And then we also need to multiply our sample size times 1 minus the hypothesized proportion. And we obtain 364.8. So both of those are at least 10. So we are good to go on the normality front. We can say it's safe to assume that our test statistic has an approximately normal distribution. right? So these are calculations that you would actually want to show as you go through this step. Right, next, was no more than 10% of the population sampled. So one way to write it is the expression I showed you on the previous 2 slides ago. But if you divide both sides by 0.1, we can think about it another way. So our sample size divided by 0.1, is that less than or equal to the population size? Okay, so if n is 380 and we divide it by 0.1, that would give us 3,800. So we want the population to be at least 3,800 people. Okay. Our sample consists of people who are trying to quit smoking using Chantix. So the corresponding population is all people who try to quit smoking using Chantix. As long as there's at least 3,800 of them, then we can assume independence. That's probably safe to say. This is a drug that is available nationwide. All right. Lastly, these people in the study, how were they selected? Were they selected at random from the whole population? Well, all it says is a study of 380 smokers who tried quitting, assisted by Chantix. It doesn't say how they were picked. We don't know if they all lived in one particular area of the country or if they were all a certain age bracket. Just not a lot of information here. So we will go ahead and assume for now, in the absence of any evidence to the contrary, we'll assume that they're representative of the whole population. If later, though, we find out that, maybe they were only people in their, 50 years old and above, then our inference would only be good for that age group. Okay, now we're ready for the mathy part. So in step 4, we're going to calculate our test statistic. So we'll use our sample data and plug it into the appropriate formula. So remember, p hat is our sample proportion. So this tells us that 53 out of 380 people in the sample were successfully able to quit, which is about 0.139. So that's going to go here in this formula. We're going to subtract from that the hypothesized proportion, 0.04, and then divide by this big guy, which you might remember, maybe not, but I'll remind you, it's the standard error of this population proportion. Standard error of the sample proportion, which describes how spread out the sampling distribution would be for p hat. So essentially, we're taking a z-score for our sample proportion. We're saying, okay, well, what if the proportion really were 0.04? How does our actual observed results stack up to that? All right, so examining the top, we see that our sample proportion was indeed a little higher than 4%, than 0.04. So we have a positive difference. So yes, in this study, the proportion who quit successfully was greater than 0.04. But is it significantly above 0.04? That's what we want to know. Well, that's going to depend on the sampling variability that we'd expect to see. How much will the p hat change just due to random chance? All right, so that's what the bottom tells us. All right, so we divide and we obtain a z-score or a z-statistic of 9.85. Okay. So that's step 4, just show that calculation. All right, so we're getting to my favorite step. It's all coming together now. So remember we said in video number 1 that the null hypothesis has to make a specific and testable prediction. So that is, it's saying, okay, what if p were 0.04? And we collect lots of samples, compute lots of p hats. How would they be laid out? So on average, we'd obtain a z-score of 0. So that would happen if we had 0.04 minus 0.04 on top of that fraction here. Sometimes we'd get a little above just due to chance. Sometimes we'd get a little below due to chance. But we're going to look at our sample data and see, is it notable in the direction that we predicted? Remember what we got? We got 9.85. So how does that line up with this? Not very well. So 9.85 is way, way over here. We're off the charts. So our observed test statistic, based on our sample data, is way over here. All right, so the general idea is, hey, we just observed something that does not line up really at all with what the null hypothesis predicted. If the null hypothesis were true, we'd expect to be somewhere, probably between plus or minus 2, or at least between plus or minus 3. All right, so in step 5, we're going to quantify how unusual is this result by calculating a probability that we call a p-value. So this is a very important definition. So the p-value is a probability which assumes that the null hypothesis is true. So that is, we temporarily pretend, what if p were 0.04? What would we expect? So assuming that's true, what's the probability of obtaining a test statistic? Remember, we got z equals 9.85. That's at least as extreme in the direction of the alternative hypothesis as what was observed. Now, what do I mean by at least as extreme in the direction of the alternative hypothesis? Well, our alternative hypothesis here predicted that the proportion was going to be above 0.04 because we thought, a greater proportion of people would be able to quit smoking. So think of this inequality as a little arrowhead. It's pointing to the right. So our p-value here is going to be on the right-hand side of this distribution. That is, our test statistic and the area under the z-curve to the right. That will be our p-value. All right, so I'm sure everybody in Stat 1 found the area under different parts of the z-curve. Just at a glance, I can tell you that this right tail way over here is going to be pretty close to 0. Now, some classes use the calculator function like normal CDF to find that area. Other classes might have used a statistics table. If you use the normal CDF function, you would be starting at 9.85, the test statistic, and going to the right, so to positive infinity or a very large positive number. And that's on the standard normal z distribution, whose mean is 0 and whose standard deviation is 1. So if you plug that into your calculator, you're going to find that it's approximately 0. Right? So that p-value is going to be our measure of the evidence against the null hypothesis. That leads us to step 6. Okay, we've measured the evidence. In this case, our p-value was approximately 0. What does that say about the plausibility of the null hypothesis? All right, so step 6 is actually quite easy. We have a rule. Just memorize this rule and you'll always come to the right conclusion. So if the p-value is less than or equal to the significance level that we picked in step 2, that's when we can reject the null hypothesis. Whereas if the p-value is greater than the significance level, that's when we fail to reject the null hypothesis. So what should we do here? Well, we obtained a p-value of approximately 0. That is indeed less than or equal to 0.05, which we picked in step 2. So the decision that should be reached here in step 6 is to reject the null hypothesis. And recall, with 2 hypotheses, if we are able to reject one, the only one left can be supported. So we are supporting the alternative hypothesis here. Okay, last step. All right, we rejected the null hypothesis. What can we say? And we want to bring this back to the original situation. So avoiding statistics jargon, what can we say about quitting smoking? So here are a couple suggested templates to get your statement started. So when the null hypothesis is rejected, we can say that we found convincing evidence of something. That is, bam, we reject the null hypothesis. What's left? We can conclude there is strong enough evidence that the proportion really is above 0.04. So I might say something like, at the 5% significance level, we found convincing evidence that smokers who try quitting smoking using Chantix have a higher 6-month success rate than smokers who don't, because we've shown that the proportion is greater than 0.04. Now, I do want to explore this other thing that could happen. So let's imagine for a minute, just in an alternate universe, what if our p-value had been 0.2? Well, in that case, 0.2 is larger than 0.05. So the decision would be to fail to reject the null hypothesis. All right, so both hypotheses are still here. We could not reject the null. Basically, either is still plausible at this point. So a good way to word this without, towing or sneaking over the line and concluding that the null is true, because we don't know that for sure, we might say something like, at the 5% significance level, we did not find strong enough evidence to conclude that smokers who try quitting using Chantix have a higher 6-month success rate than smokers who don't. All right, so we did not find enough evidence. That leaves it open that, maybe the drug really doesn't work. But then again, maybe it was the fault of our test. Either we just had bad luck with a kind of unusual sample, or maybe that our sample size wasn't large enough, and had we had a larger sample size, we could have had more data and more ability to find that evidence. Okay, so that concludes our first example of the z-test for proportion. Now I just have a couple odds and ends. So we tested here what we call a one-sided test. That is, we were interested in, is the proportion larger than 0.04? We didn't concern ourselves with what if it had been less. And we had said, well, that looks like a little arrowhead pointing to the right, so we're focused on the right-hand side of the z-distribution. Okay, so that's an example of a one-tailed test, where we're looking at the right-hand side. Or some people might say a one-sided up, because we're looking up to the bigger numbers. If, though, our inequality had been pointing the other way, then our p-value would come from the other side of where our test statistic is. So we'd still call it one-tailed or one-sided, but now it would be down. It's pointing down towards the negative numbers. Lastly, remember there was a third option for an inequality that we could test. We could test does not equal. That's called the two-sided or two-tailed test. So there, our p-value would actually come from both tails. We would find the area in the tail nearest to our test statistic. So that would be the right-hand side if our test statistic is positive, or the left-hand side if our test statistic were negative. So find that area and then double it to give two tails. So it's double because they're mirror images, so they'll be the same size, each piece. Okay. Only do that, though, if the sign does not equal. All right, there is a calculator shortcut that will find the z-statistic and the p-value for you. So if you're on the TI 83 or 84, you would press Stat, then go right a couple clicks to Tests, and it's called one-prop z-test. It would ask for the hypothesized proportion, so in this case, the 0.04, the number of successes in the sample size, and then the sign in your alternative hypothesis. This one got a little blacked out by the cursor. As long as you set up the hypotheses in the way I've shown, with the parameter on the left and the number on the right, then you would just look for the matching sign. All right. In our